Okay, so let's start this morning session with the talk of Amir on the capacity of the range of a simple random walk.
Okay, so first of all, it's always a pleasure to speak here at Harvard, and it's a double pleasure to speak in a conference in honor of Raghu's contribution to our field, immense contribution to our field. And before I start with the talk, I want to share with you two points. The first is I did not start in mathematics as a professional mathematician, and my conversion to mathematics came by reading in the summer of 1989 the 5 papers of Raghu and Donsker. So thank you for converting me to be a professional probabilist first. And secondly, I gave a talk at some point. I will tell you some anecdote on my only paper written together with Raghu. I gave a talk at NYU in the probability seminar, and I said, no, I know how to do certain things. I don't know how to do other things. And after the talk, Raghu came and quietly told me, I have an idea. And that was Friday. And on Monday, I went up to the 13th floor, and I got the idea. And this was, of course, a beautiful idea. It took a few months for me and Ofer and my PhD students to work out the idea into what we needed to do for the paper. But this was a 1 hour in Raghu's office, which I learned the most mathematics per hour in my life. Okay, so thank you for that too. And I'm going to talk today on a very classical topic, 2 classical topics, extremely classical, the law of the iterated logarithm, and something involving capacity of simple random walk. This is a joint work with Izumi Okada, and I was quite surprised and humbled to learn when we did it how little we understand about this relatively classical object. So the content of the talk, I will first explain briefly what the object we are talking about, the Newtonian capacity, then motivations why we care about capacity of the range of a walk. I will go over a list of known results, which might be nice to know. Then I will talk about our contributions, the capacity of the law of the iterated logarithm, or it will not necessarily be iterated logarithm, it might be different law, but the same principle. And given time, I will talk about some elements of the proof briefly, and questions, meaning things we don't know how to do. And it's nicely marked in red on the side, so as we go on the slides, you can see where we are in the talk. Okay, so start with a Newtonian capacity. So instead of a simple random walk, let's talk about some other extremely well-known classical object, which is a d-dimensional Brownian motion. I will keep using beta for the Brownian motion, allowing it to use B for ball. So the Brownian motion, as you know, has a normal transition density, which I wrote here explicitly for you, here. And as if it's in dimension 3 or more, the Brownian motion is transient, which one manifestation of this is that the green function, which is an integral over time of the transition probability, is actually finite and is given by this nice simple formula. It's a distance, Euclidean distance, to a suitable negative power. Associated with the green function, you always have a capacity, in this case a Brownian capacity of any set in Rd, and it's given by the inverse of the minimal energy. You look at all probability measures supported on your set and try to minimize this quadratic form where the kernel is your green function. So you can see that you try to get avoided from the diagonal, really, because diagonal will contribute a lot. So that's the Newtonian capacity of the Brownian motion. Now, for simple random walk, you can do something very simple, very similar. You have the simple random walk in dimension d, and I will always walk in transient dimension greater or equal to 3. So the green function will be finite, and here it will just be the sum over the probability of finding the walk at position y if you started at x, and the sum is over all possible time indices. So it's an expected number of visits to y if you started at x. The discrete Newtonian capacity of a set in ZD is defined exactly similarly, just using G instead of G of beta. And of course, if you take X and Y very far, then G by invariance principle will be very close to G of beta, right? So it will have the same decay. Alternatively, in the discrete case, you have another way to describe the Newtonian, the capacity by looking at the sum of the probabilities starting at X of missing the set A, and you sum over all the point in X. So you take one walk, and you start at every different point of your set and see whether you miss the set or not. Now, there are few elementary property of the capacity which follow immediately from the definition, because both the random walk and the Brownian motion are invariant. They have increments which are invariant to translation. You can see that translating your set by a constant will make no impact on your capacity. So you can always center the set. It has no effect. You can also see that the capacity is monotone in the size of the set. This comes by the definition with the support. So if you take a bigger set, you always will get a bigger capacity. But if you take a union of two sets, it's a sub-additive quantity. You get less than the sum of the two, because, for example, if you look at the avoidance probabilities, there is a chance that you start at A and you hit B instead of hitting A again. So it's a sub-additive, monotone increasing, invariant to translation. Our goal is to study the asymptotic of the capacity, but the capacity of a random set. The random set is going to be the set of points that a simple random walk, transient simple random walk, is visiting in its first n steps. Right? So it's a range of the random walk. You don't care the times, but you just look at the capacity of this set, and you are interested in the asymptotics as n goes to infinity. So what does it mean we are interested in the asymptotics? Like typically in probability, you will be asking all sorts of limit theorems. You might ask about law of large numbers, strong law. You might ask about fluctuations, central limit theorem. You might ask about large deviations, and we will ask about law of the iterated logarithm. The law of large numbers and the central limit theorem for this object are known. They have been done by a group of Sela, Shapira, and Susi in the last decade. It's not so recent. The goal is to extend, or our goal in this paper was to extend to the law of the iterated logarithm these two results. The problem of the large deviation, the rate is known, but the rate function is not known. It may not have a nice formula. It's not clear whether. Certain regimes are known, but very little is known. As you go more from the center to the tail, things are more sensitive and might be more difficult to do.
So this capacity you want to compute here is the discrete one for a random walk?
Mostly the discrete one. In some cases, it implies as a corollary the results for the continuous one. Okay, so what is the motivation? Two motivations. One is the capacity of the range of the random walk is related to intersection of two independent simple random walk, which is a subject of its own big topic and interest. My motivation will mostly be B. There is a strange but very consistent relation between the asymptotics of the capacity of simple random walk and the volume of the simple random walk in 2 dimensions less. And the way that theorems about the capacity go is always to read first the paper on the theorem on the volume, and then copy the proof, but adapt it, because it's more complicated. But there is no direct relation. So what we wanted to see is whether in the LIL it actually goes on or breaks down, and to get a better understanding of this relation. So first, let me give you the motivation, the connection to intersection of simple random walk. So it is well known that the probability of missing a set A if you start at X far away, and the set A is kind of centered at 0, has a decay like X to the minus D minus 2, and the coefficient in front is really controlled by the Newtonian capacity of the set A, the one that comes from the Brownian motion. But you have the same idea also for random walk. Now, if you take the particular set we are interested in and plug A for this particular random set and take an extra expectation, what you see is that what you will get this deterministic constant times the expected value of the capacity of Rn. Now, what is written on the left can also be interpreted as a probability of a simple random walk that start at 0, that's the one that is in Rn, and running for until time n, to not intersect another simple random walk that starts at x and running until infinity. That's exactly the same object. I just expressed it in words. So if you don't take x very large, so this is not true, but if you take for a moment x equal to 0, and you take 1 minus this object on the left, what you get is the probability of the intersection of two random walks being empty. So the asymptotic of the probability of intersection of two random walks, one infinite and one long, being empty, is related to this object at 0, which is related to this object, but only when you take x to infinity. So modulo this fudging, this study of this can give you information on that. But there was a fudging done here. The second motivation is more clear, I think, and more concrete. You look at the volume of the same random set. So volume means just you look at the number of distinct points in this set. The random walk might visit the same place twice, so you don't count it. You just count the number of visited points. And in all known results, you have the following theorem, meta-theorem. You look at the theorem, the asymptotics for the d-2-dimensional simple random walk volume. You look at the theorem for the d-dimensional simple random walk capacity, and it's the same theorem, essentially. Modulo constants, but the same scale, same type of result. I will show you the list, and you will get to appreciate. And the big question is whether this is coincidence. Do we have some kind of a magical mapping relating this to object, or because the proofs are also following similar lines. Now, we want to compare the result for LIL for the volume, which was known already, with the new result we got for the capacity. And for your convenience, whenever there is a capacity, I will use a magenta color, and whenever there is a volume, I will use a teal color. So you can see on the slides. Okay, before we do that, what are the properties of the volume? Volume has exactly the same properties as a capacity. If you shift the set by a constant, the number of points in the set does not matter. Volume is obviously sub-additive, and volume is obviously monotone. If you increase the set, you get more points, and if you take a union, you may not take the same. Now, one characteristic property of the volume which helps you a lot, that if you take two distinct points, then it's additive. This is not true for capacity, because even if you take two distinct sets, if you start here, you might hit the other set with a random walk. So this makes proof for capacity more annoying / complicated. And if you look at the literature, you will also see there is like a 30-year gap between the theorems done. Okay, so here is what I meant by the relationship, at least qualitatively, between the known results d-2 for volume and d for capacity. So if you look at the type of result you have, for the range of random walk, by Donsker invariance principle, the dominant part for the range of random walk is really going to relate to the maximum of the Brownian motion. So the dominant part is a random variable coming from Brownian motion. Very similar, the dominant part for the capacity of the range of the random walk in dimension 3 is going to be dominated, is going to relate to the capacity of 3-dimensional Brownian motion, and the dominant term is going to be random, not constant. If, however, you move dimension by 1, you get strong laws starting at dimension 2, and here strong laws starting at dimension 4. If you subtract the mean, or the leading term, and look for non-degenerate limit theorem, that for simplicity I call central limit theorem even if they are not Gaussian, you find that you have a genuine Gaussian central limit theorem for the volume starting at dimension 3, but you have a non-Gaussian limit in dimension 2, and very similarly here, 2 replaced by 4 and 3 replaced by 5 or more. So just add 2 and you get the same result.
The non-Gaussian thing is?
It's very similar. We'll get there. We're going first general, now more specific. So here are the results on Donsker invariance principle for the volume of random walk and capacity of the range. So the volume of random walk, very simple, is this is just the maximum minus the minimum of the random walk, what you see, because it's just an interval. Divide by square root of n, you will get the volume of the Brownian motion from 0 to 1. It's very simple. Convergence. Result of Chang, see, quite recent relatively. In dimension 3, if you divide the capacity of the range of the walk by square root of n, and you take the limiting distribution, you will get the capacity related to the kernel of the Brownian motion of the 3-dimensional Brownian motion run from 0 to 1. you have the term 1 over 3 over square root of 3. This comes because the connection is not correct because a simple random walk makes a step only in one direction every time, at least the one we usually use, but the Brownian motion goes in all 3 dimensions. So if you want to get rid of that, you need to take a simple random walk that jumps in all 3 dimensions at the same time. And then you just eliminate this constant. If you look at strong laws, so in any dimension, this is a classical result going back at least to Spitzer, in any dimension, the volume divided by n by subadditivity converges to a non-degenerate constant almost surely. To a constant almost surely. This constant will be 0 in dimension 1 and 2 in the recurrent dimensions, but will be strictly positive starting in dimension 3. If you go to the capacity, this is classical work of Chain and Ori from 1970, you have exactly the same subadditivity, the same almost sure limit, and what the paper do, they do provide estimates to show that the constant is going to be strictly positive if and only if dimension is greater or equal to 5. So again, you added 2 to 3, you got 5. If you look at more exciting or quantitative results, you can look at strong laws and central limit theorems for the volume in dimension 2. In dimension 2, you know that dividing by n is not the right scale. The right scale to divide by the volume is to divide by n over log n. This is a classical result of Dvoretsky and Erdos from 1951. You get this particular constant in the limit. And a result of Legal from 1986. If you subtract from the volume the expected value, then now you need to scale not by n over log n by n over log n square, and you will get yourself a non-Gaussian limit variable, which is related to the self-intersection local time of the Brownian motion. This is really the self-intersection local time of the Brownian motion normalized. Self-intersection of local time has to be defined correctly. If you look at this definition, formally it makes no sense, but you do it with dyadic approximation, and you read Legal, beautiful paper, and then you know everything. This is how I know this stuff. If you go many years into the future, or into the past, but recent past, to 2019, Asela, Shapira, and Susi repeated this type of work in dimension 4, the law of large numbers. You again divide by n over log n, you get another constant. If you subtract the mean, the scaling is going to be log n square, and you get a new object, but very similar one. It's really like the self-intersection, but you replaced the self-intersection with a green function of the 2 times. And you, of course, subtract it, and this is also a singular thing, so you define it in the usual way, exactly the same way that you define for the capacity. Okay, you can also look at real central limit theorem, or limit theorems, now in dimensions 3 and greater or equal to 4. This is a classical, for the volume, it's a classical work of Jane and Pruitt from 1970, that if you subtract from the volume the mean, the limit, the constant times the n, and you divide suitably, in dimension 4 you divide by square root of n, like a classical central limit. In dimension 3 you have a logarithmic correction term because certain variables you add have too big tail. You get yourself the nice normal law. Similarly, works of Asela, Shapira, Susi, and Shapira in 2018 and 21 repeats the same thing, just replace 3 by 5, 4 by 6, and change your constants. I mean, you have to prove it. It's very easy to write the theorems if you don't have to prove it. Otherwise, you have to read the paper. The proofs are, of course, more involved, which is a reason for the delay in their appearance. Okay, so here is a summary of what I said before. You have the Donsker invariance principle for volume in dimension 1, for capacity in dimension 3. You have the strong law starting in dimension 2 for the volume and starting in dimension 4 for the capacity. You have a non-Gaussian limit law, dimension 2 for volume, dimension 4 for capacity. You have a central limit theorem, dimensions 3 or more for Gaussian, for volume, dimension 5 or more for capacity. And for the LIL, we claim that we will get the same result, more or less. That the volume, LIL for volume in dimension d minus 2 will translate into LIL for capacity in dimension d, and we will have different behavior between 2 here, 3 and 4 or more, and so here it will be 3, 4, and 5 or more. 3 different regimes corresponding to what we see for the volume. And in order to describe this, now I will use the following slightly misleading short notation. When you have a log with something underneath, this is not the base of the log, but it's a number of logs you take. Because I will have 2 logs and then 3 logs and maybe more logs, so just to be on the safe side. Okay, so classical LIL, well, now we are going really back into the history, all the way to Kinchin in 1929, and the corresponding LIA of Kai-Lai Chang in 1948. If you take the volume, if you divide by square root n log n, to log n, that's where the name LIL come from, take the lim sup, you get 1. If you want to look at the minimum of the volume, or the range, try to make the maximum of the random walk more in 1 dimension smaller, instead of multiplying by double log, you divide by double log. That's a Kinchin one, and you get the same limit. So you have the lim-ins, the lim-sup behavior, and they are done like that. Okay, what happened in dimension 3 for the capacity? More or less the same. More or less, but not exactly. If you divide the capacity by a suitable function, the lim-sup will go to 1 in dimension 3. If you divide the capacity by another function, the lim-inf will go to 1. If you ignore the constant, the function for the lim-inf is exactly the one you saw for the volume. It's n over log n. The function for the lim-sup is n times log n, but surprisingly, there is a division by a log cube of n. But I am going to claim that this is an artifact, just to be, okay, it's a big artifact, but it's an artifact. It's not really changing the picture that things are the same. And I will explain where it comes from very soon. A corollary of this is, of course, that you can, because you have invariance principle in these cases, you can just replace your result and write a result for Brownian motion. And actually, one way to prove it is to do the proof of the Brownian motion. So in this case, you are free to prove either above or below and make the conclusion as you wish. Okay, let's go to dimension greater or equal to 2 and see what known for the LIL for the volume. The results for the LIL are actually more recent than, for dimension 4 or more, the results are very easy, and they are classical Jane and Pruitt, because in dimension 4 or more, you behave more or less like sums of independent variables. But in dimension 2 and 3, the results are more complicated, and they come from a work of Bass, Chen, and Kumagai in 2002 for dimension 2, and Bass and Chen and Rosen in 2009. And what are the results? Well, in dimensions 2 or more, you need to subtract the mean, because you have a leading contribution from the mean. And then you normalize. You normalize by something which goes slower than this normalization for central limit theorem, because you are looking at the asymptotic, almost sure fluctuation coming from Borel-Cantelli type results. And then, depending on the function you normalize, you get the lim-sup and the lim-inf, and they are 1 or minus 1 in the usual way. And here are the functions which I gave you. So this is these are the functions. Whatever they are, these are the functions. Now, the point is, as I said, in dimension 4 or more, you really get the usual LIL. In dimension 3, you have a correction term because of the lack of moments. And in dimension 2, it's very different functions for them lower and the upper, because it's not really a sum of independent variables, very far from it, which is the reason why it took 30 years to do it. This is infinitely easier than the other ones. So this is what is known. What happened for the capacity, and here you have to trust me that the functions are the same, but look at these. The functions are exactly the same. Constants are different. And in our work, we show that, again, you just move d by 2 more. 2 goes to 4, 5, 3 goes to 5, and the rest of it goes to 6 or higher. And you have the same scaling. You subtract the expected value, normalize, you get 1 or minus 1. So the coincidence is preserved at the level of the LIL, up to changing various constants. We did not learn from it why the coincidence is preserved, because all our proofs were read the proof of that, find a clever way to adapt it to a more complicated thing, and then repeat it. So I already give you a hint. Okay, so the results, as I said, are that in dimension greater or equal to 4 of LIL for volume dimension D minus 2 scales like LIL in dimension Rn at D. In dimension 3, this correspondence breaks down in the case of the limb soup, but I will explain why it breaks down and why you should not be that worried about it. Now, in the process of doing that, we also predict that the limb soup for the capacity in dimension 3 is obtained by making the random walk look like a cylinder. In one dimension, it is elongated. And that's what gives rise to a larger capacity. 2 dimensions go the usual scaling, and 1 dimension, not necessarily x or y, but one random dimension possibly, is getting elongated. And that gives you the capacity, we claim, and the result for the limb inf, we predict the scaling is making the simple random walk look like a ball compressed, because the ball has a minimum surface area to volume, or minimum capacity also to volume. Now, this does not mean that we say that this is really a ball, or this, you should understand it in the way that Shurov defines, right? In a loose way. It looks in some sense like a ball or a cylinder. And I will explain what I mean more or less by that. Now, here is what I mean. You can calculate what happened to the maximum. It's a very simple exercise. You can calculate what is the limb sup and the limb inf of the maximum of the norm of a simple random walk in dimension 3, and you get yourself suitable scaling functions with LIL, with a suitable constant, and you find the limb sup behave like that and the limb inf behave like that. And this corresponds what I call a cylinder domain, and this corresponds, you can check, to a ball domain, meaning to get the norm to be small, you need to make all dimensions small. To make the norm large, the less costly way is just to expand in one direction. There is no need to expand in all 3 directions. Now, you can also calculate the capacity. Something we can prove also is that at the same time, you have infinitely many points in your sequence. If you do a random walk running from 1 to infinity, you have infinitely many points where both the maximum of the norm is close to its maximum, and the capacity is close to the value of the LIL. So you can achieve the right capacity for the LIL by expanding the maximum infinitely often. It doesn't mean that this is the only mechanism. This is something we don't know how to prove. We believe it is the only mechanism, but we don't know how to prove it. But we know that this is good enough mechanism, and similarly for the minimum. If you compress, you get the right capacity. So that's what I mean by predicting cylinder and ball-like domain for large and small capacity. To prove the result, I need to prove a conditional result, that if you do not have this property, you will not have that property. This I don't know. It's a much stronger statement. Okay, and I will explain to you the strategy of the proof of proving the LIL in dimension greater or equal to 4. One key idea to do it in dimension 3, and then few key ideas for the limb sup in dimension 3, and then I will prove you the whole lower bound for the limb inf, because you can understand this is a quite easy thing because I do the whole proof. Okay. So first, what is the strategy to deal with the capacity in dimensions greater or equal to 4? The strategy is as follows. You can break the capacity in an interval from 0 to n to pieces of the capacity, corresponding to pieces of the simple random walk. So you define UAB as the capacity related to only the steps of the random walk from time A to time B. If you sum those things over disjoint intervals, you have here independent random variables, because the steps of the random walk, remember the beginning doesn't matter, we can always shift everything. The steps of the random walk are independent of each other. So this red, the sum of the red variable, is something we really like. We love those things. We love sums of independent variables. So if the capacity was written like this sum of the red thing, then life will be beautiful, because we know how to do LIL for sums of independent variables. Even if the independent variables are not identically distributed, we know how to do that. But the capacity is not that. You have to correct for the interaction between your pieces, and this is a way to correct for the interaction between your pieces. It's really the result for the large union minus the sum of the two. And because of subadditivity, this contribution is a non-negative variable. So you have the sum of independent variables minus the sums of non-negative variables.
In the case of the volume, the blue thing would be 0
Yes. No, no, in the case of the one, it's not. No, because you can come back. These are the steps of to get independent, these are the steps of the random walk corresponding to different time, not different places in space. Otherwise, they will not be independent. But what you like to do is to cancel this, and in dimension 5 or more, this is exactly what happens. This becomes negligible, and your walk is very nice because you have a sum of independent variables. Of course, for the capacity, we need to subtract. You need to center them, right? We need to subtract the mean, but we can subtract the mean of each one. So that's why in dimension 5 or more, walk is relatively easy. In dimension 4, on the contrary, this is negligible, the sum of independent variables. All you have is this complicated-looking object, which is why dimension 4 is much harder. And that was exactly the same story in the volume. That's why volume in dimension 2, LIL was difficult. This work of Bass and Kumagai is a very beautiful work. Recommended to everyone to read it. Okay, so what do we do for the capacity in LIL in dimension 4? Well, after some work, which I will save you the trouble of understanding, if you choose break this NK into a suitable subsequence, which is not a linear one, but you follow Bass and Kumagai subsequence and you see what subsequence to use, then you get that the contribution of what you care, the other one is negligible, is very easy to prove, is becoming really some quadratic form involving the green function for two different random walk. And this is good because this is exactly the object that you saw appearing in the limit theorem, so you are not very surprised about that. And now what you need to do, you need a lemma to control tail of sums of green function of these things. This green function is singular, so if SI is close to SI tilde, that's a problem for you. But you need to calculate the moments, and then we bound the moments. Bounding the moments suitably give you a bound on the moment generating function, and that's good enough to get you enough tail to do an LIL by Borel-Cantelli 1 and 2. That's the key idea. What you need to do is to do this lemma. And the constant, you can get even the suitable constant. It's related to this was a follow-up work of Okada, my co-author, and Arka Adhikari. They calculated the blow-up of exactly where the moment-generating function blowed up and got the right constant out of it. It's related to a nice constant in analysis, and it's a very nice work, but much more difficult because instead of upper bound, you need to do it perfectly. So lots of counting and combinatorics. Okay, what do you do in dimension 3? So in dimension 3, you upper bound the estimate, you get an upper bound to estimate of capacity of Rn by understanding what shapes the simple random walk can have and bounding what happened when the simple random walk has a certain particular shape. And for the lower bound, you approximate by looking at the probability to get a cylinder shape, like I explained to you. Just take a particular direction, expand it. You know that this already happened up to a n, and calculate the capacity. And the extra log n cube that you find is simply coming by calculating the capacity of a cylinder. If you calculate the capacity of a cylinder of size, high size, square root of n in 2 dimensions, and slightly bigger in the 3rd dimension, there is an extra log n cube that comes there. So it's just coming from this calculation. If you want coming from some analysis calculation, you can ignore it. It's not telling you anything about the random behavior of the object. Now, the way that you do this calculation, what you need is a lemma, and this lemma is after very similar result appear in the work of Jane and Ori already in 1968, that tells you that you can calculate bound the capacity of a set, and just any deterministic set, by more or less, the leading term is the size of the set, but what you need to divide by relates to the sum of the green, look at the green function of those points as a matrix, and just look at the norm bound, row and column bound, and if these sums are more or less constant, if they don't change too much with respect to the first index, then you see that you have a very tight bound. And the good news is that calculating asymptotics for such things, for plugging in values of the simple random walk, is just a pairwise interaction. It's much better than calculating the capacity in terms of analysis. So that's how we go about doing all these bounds. We first use this lemma, and then we follow up with a very careful work on this sum of squares. For the lim-inf, you have a nicer, easier result. You can use the work of Vandenberg, Van Hofstad, and Bolthausen in 2001 that prove the result for the volume of a suitably scaled Wiener sausage. This is a Brownian motion run up to time n over 3, but then you expand it with a ball and calculate the volume of what you get. So they studied the tail of the volume of the Wiener sausage in dimension 3, and you get from this result about the lim-inf. And then you can use the Poincaré-Karlman-Szego theorem that tells you that the infimum of the capacity of any set given the volume is a capacity corresponding to the ball. This is not Brownian, but ball. And this is equal to 2 pi. And you can combine the two to get yourself immediately a lower bound for the capacity in the Brownian case. And because of invariant principle, this will translate to the random walk. Okay, so I finish with my questions of what is not known. Okay, what is a very good idea to do, if anybody can do that, is to show a direct relation or some explanation that does not go read the proof on the left and copy and write another paper on the right, on the relationship between why the volume in dimension d minus 2 gives you rise to exactly the same asymptotics for the capacity in dimension d. We did not learn. We only learned that this extends more. And now I am more certain that there is some mathematics that should explain it, because it's not only the numbers that change, but also the behavior, what dominates what you can neglect, how you construct the proof, what you approximate by. They're all the same. So it must be that you have underlying the same structure. It's not just coincidence. Now, there are a few other general extensions. All this work was only for the poor simple random walk. As you know, there are many other random walks. And because this is involving the capacity, it involves repeats, it's not related so much to the size of the increment, but rather to the graph, to what you repeat. It, of course, what is relevant here is only lattice-type random walk, because if you take random walk with Gaussian increments, you will not visit anything. Or you define the capacity now differently, so you take into account distances. But anyway, so we don't know how to do it for more general random walk, although maybe this is only technical, I'm not sure. You can also look at a more exciting object, like a random walk on a group, and then you can take non-commutative non-commuting group, which same story you can try to do. The problem of large deviation is more or less open. There are very few works of Sela and Shapira, which kind of nibble on it, but most of it is not known. Even for the volume, certain things are not known. You usually start by looking at the volume, and if it's not known, you don't continue, because there is no point. But if it's known, then you can try to continue. And you can take other stochastic processes. For example, for critical branching random walk, certain things have been done already by Shapira and relating again the volume of the random set, but it's not, Rn now is not the range of the simple random walk, but it's a range of the critical branching random walk in dimension d minus 2, capacity in dimension d. You can ask, what is done was law of large numbers. You might say central limit theorem, LIL probably going to go the same. You can also verify our geometric prediction that the lim sup is actually attained at a cylinder-like or attained at a ball-like. Again, we have indication, but we don't know how to prove it. And in general, you can ask what shape will appear for simple random walk on other graphs. We only dealt with ZD. That's not a lot of graphs. Thank you for your attention.